what I want to do in this video is to talk about nucleophilicity. 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 And this is really just how good of a nucleophile something is. Or I'll just make up a definition right now. The ability for an atom, let me say an atom, let me write this, atom slash ion slash molecule to act as a nucleophile or to give away extra, I'll write that in quotes, extra electron and bond with a nucleus or with something else. I'll say with a nucleus. Let me say with and I'll just say and bond, but that's, I want to say with a nucleus because that's what nucleophilicity is saying. It loves nucleuses, especially positive ones, then it can give its extra electron to it. Now, as a first cut, if you want to identify a good nucleophile, it should have extra electrons to give away. So it should have extra electrons to give away. So have extra electrons to give away. And the best things that have extra electrons to give away are negative ions or anions. So if you were just at a very high level, something like the fluoride anion. Normally, fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. But it's so electronegative, it might be able to swipe off another electron from something else, and then it becomes the fluoride anion. So then it becomes the fluoride anion with a negative charge. And you can do that for all of the halides. You could do that for chlorine, can become chloride. Bromine can be bromide. Iodine could be iodide. Let me do iodine too. So iodine, once again, it's a halide. It has 7 valence electrons. It has many, many more electrons than fluorine. But if you just look at its valence shell, it has 7 electrons. And then it is also reasonably electronegative, not as electronegative as fluorine. Remember, the trend goes like this, from the bottom left to the top right. So fluorine is extremely electronegative, but iodine is still pretty electronegative. It is a halogen, so it also might be able to swipe off an electron from someone else and become iodide. So in general, things with extra electrons, lone pairs of electrons, and especially a negative charge are going to be pretty good. Nucleophiles. And another example that's not a halide is the hydroxide anion. So OH, and this is an example of something that is a molecule. So OH, maybe traditionally water would look like this. So traditionally, this is just neutral water. And oxygen has 2 lone pairs like that, but oxygen is pretty electronegative. It is already kind of taking the electrons away from one of the hydrogens, and at some point it might just take it all together, and then you have the hydroxide. And then you have the hydroxide anion. So this will look like this. So you have your original 2 lone pairs just like that, and then you have this pair that's going to be taken. It already had that electron, and it takes that electron from the hydrogen, so now it has 2 more electrons. Let me color code it so you see what it took. It took this electron from the hydrogen, and now this also has a negative charge. That's also a reasonably good nucleophile. And of course, you have your hydrogen now. It lost its 1 electron. It only has a proton in its nucleus. So it's just, when you ever see H+, this is really just a proton. There's nothing else to that hydrogen. So that's hydroxide. So these are all reasonably good nucleophiles, and that they have something to give away. They have extra charge. Now, what I want to do is think about between these, how do you think about what's going to be a stronger or weaker nucleophile? And here, it becomes a little bit more nuanced. And what we're going to do is differentiate what happens in a protic solvent versus what happens in an aprotic solvent. So let me start with a protic solvent. Protic solvent. I'll make 2 columns here. Protic solvent, and then we'll do aprotic solvent. Aprotic solvent. right over here. And once again, these are fancy words, but they mean something pretty simple. Protic solvent is something that has hydrogens that can be taken away, or it might have free protons flowing around. An example of a protic solvent is water, or really any alcohol. So water is the simplest example, or maybe the most common. And the reason why we call it, why you might have protons floating around, is exactly this little reaction I showed right here. Maybe every now and then, hydroxide anion forms, or even more likely, maybe a water takes a hydrogen from one of the other waters. One of the water molecules takes hydrogen from one of the other water molecules and becomes a hydronium, where it's not a proton necessarily, but it's an oxygen. It's an oxygen that has, so let's say if you start with water, and this one of these electrons were to be given to some proton floating around, it would look like this. And it has a positive charge. And then this proton is very available. It's kind of, you can almost imagine it's almost floating around, because that oxygen really wants to take back that electron. So protic solvent is water. In water, you might see a little bit of hydroxide, a little bit of proton, a little bit of hydronium. You see all of it in there. But the bottom line is that there are protons that can react with other things. You have protons that can react with other things. Let me clear this away so that I have some real estate. So let me just write down water. So water is a protic solvent. Now, you might say, hey, wait, is that always the case? You know, it seems like hydrogens are everywhere. Well, no, it's not always the case. Let me show you an aprotic solvent. So diethyl ether looks like this. Diethyl ether looks like this. And just so you know the naming, it's an ether because it has an oxygen, and it's diethyl because it has two ethyl groups. That's one ethyl group right there, and that is the second. So it's diethyl ether. Now, you might say, hey, this guy's got hydrogens lying around as well. Maybe those can get released. But no, these hydrogens are bonded to the carbon, and carbon is not anywhere near as electronegative as oxygen. So these are not going to be, carbon is unlikely to steal these hydrogens' electrons and these hydrogens to be loose. If they were bonded to the oxygen, that would have been a possibility. So in water, you have, obviously you have HOH. In alcohols, you have some maybe carbon chain bonded to an oxygen, which is then bonded to a hydrogen. So in either of these cases, in either water or alcohol, you have these hydrogens where the electron might be taken by the oxygen because it's so electronegative, and then the hydrogen floats around. Anyway, that's a review of protic versus aprotic. Now, in a protic solvent, and this is actually a general rule of thumb, if a nucleophile is likely to react with its solvent, it will be bad at being a nucleophile. And think about it. If it's reacting with the solvent, it's not going to be able to do this. It's not going to be able to give its electrons away to what it needs to give it away, to maybe, what we saw in, say, an SN2 type reaction. So in a protic solvent, what happens is the things that are really electronegative and really small, like a fluoride anion. So let me draw a fluoride anion. A fluoride anion in a protic solvent, what's going to happen is it's going to be blocked by hydrogen bonds. So it's very negative, right? It has a negative charge, and it's also tightly packed. As you can see right here, as its electrons are very close, tied in. It's a much smaller atom, or ion in this case. And if we looked at iodide has 53 electrons, many orbitals. Fluoride, or actually iodide would have 54. It had the same as iodine plus 1. Fluoride will have 10 electrons, 9 from fluorine, plus it gains another one. So it's much smaller. It's a much smaller atom. And so when you have water hanging around it, let's say you have something like water, that has a negative charge. Water is polar. Water is polar. And actually, both of these are polar. So I should write down polar for both of this. This is a polar protic solvent. This is a polar aprotic solvent. In this case, water is still more electronegative than the carbon, so it still has a partial negative charge. These parts still have a partial negative. Water still has partial negative. The hydrogen has a partial positive charge, so it is going to be attracted to the fluorine. And this is going to happen all around the fluorine. And if these waters are attracted to the fluorine and kind of forming a shell, a tight shell around it, it makes it hard for fluorine to react. Hard to react. react. So it's a worse nucleophile than, say, iodide or hydroxide in a polar protic solvent. Hydroxide has the same issue. It's still forming hydrogen bonds. But if you wanted to compare them, iodide is a much bigger, maybe I draw it like this. I'll draw its valence shell like this. It's a much bigger ion. It has all these electrons in here. And so it still will form hydrogen bonds with the water. It still will form hydrogen bonds with the hydrogen end of the water because they're partially positive, but it's going to be less tightly packed. And on top of that, iodide is more polarizable. It's more polarizable. So this is polarizable, which means that its electron crowd is so big, and the valence electrons are so far away from the nucleus that they can be influenced by things and then be more likely to react. So let's say this iodide is getting close to a carbon that has a partial positive charge. So let's say a carbon is attached to a, it's attached to a bromine, and then it's attached to 3 hydrogens. We've seen this will have a partial negative charge. It's more electronegative than the carbon, which will have a partial positive charge. And so when this big guy with the electrons really far away, gets close to this, the electrons are more of the electron cloud is going to be attracted to the partial positive charge, so it'll get distorted a little bit. And so it is more likely to react in a polar protic solvent. Fluoride, on the other hand, very tightly packed, blocked by the hydrogen bonds, less likely to react. So if you were to look at the periodic table, if you look at, say, just the halogens, in a polar protic solvent, the halides, so this would be the ion version of the halogens, the halides, iodide will be the best nucleophile, fluoride will be the worst. So in a polar protic solvent, so let me write this down. In polar protic solvent, in a new color, polar protic solvent, then we have a situation where the iodide is the best nucleophile, iodide followed by bromide, followed by chloride, and then last of all is the fluoride. Now, the exact opposite is true in a aprotic solvent. In an aprotic solvent, the fluoride, which is, fluorine is far more electronegative. Fluoride is more basic. It will be more stable if it is able to form a bond with something than iodide. Iodide is pretty stable. It's actually, if you look at hydrogen iodide is actually a highly acidic molecule. So iodide itself, the conjugate base of hydrogen iodide, is going to be a very bad base. So when you're dealing with an aprotic solvent, you go in the direction of basicity. And we're going to learn in the next video that actually basicity and nucleophilicity are related, but they aren't the same concept. And we're going to talk about that in a little bit. So, but if you're in an aprotic solvent, you're no longer as light, you're not reacting with the solvent as much. And in this situation, fluoride is actually the best nucleophile, followed by chloride, followed by bromide, followed by iodide. So here you're going in the direction of basicity. This is the best, this is the worst in an aprotic solvent. If it was in a protic solvent, this is flipped around. This becomes the best, and this becomes the worst.